Homework 5, problem 8. Find the magnetic field B and its first three derivatives with respect to Z at this distance D, at this point here, that's halfway between the two loops, where the distance D is the separation of the two loops. The next question is, at what distance D do the first three derivatives vanish? Now, in order to do this, we've already done the magnetic field for a single loop. That was in problem 6, so we're just going to use that again. And so, copying that down here, we're going to get the magnetic field B, as a function of R, is going to be mu naught I over 2 times, and now we're going to have to be a little bit creative here. This is going to be I'm going to ask this as a function of, here, let's use a different color so we can see it better. As a function of a general distance Z, okay? Z, I'm going to ask this as a function of a general distance Z because I want to be able to take the derivatives, and if I want it in terms of the derivatives, I have to have it in a functional form. So, back to the problem. This is a squared over the square root of a squared plus z squared to the 3/2 power plus, same thing, a squared, but now I need the distance from this loop. And the distance from this loop is plus d minus z quantity squared to the 3/2 power. Okay. So this is the general solution for the magnetic field z hat. Okay, for the magnetic field along the axis between these two loops. The question that we have here is, now let's take derivatives. But I want to, before doing that, look at one of the symmetries of this problem. I've talked about symmetries a lot. Well, here's an interesting one. This is a function of z, and this is the same function of quantity d minus z. When I take derivatives, so when I look at partial over partial z of f of z, I'm just going to call that f prime, okay, evaluated at z. When I look at partial derivative of z of f of quantity d minus z, by the chain rule, this is going to be f prime evaluated at d minus z times the derivative, partial derivative of what was inside. But the derivative here is just minus 1. And so this is going to be minus f prime evaluated at d minus z. And I can use this symmetry, right, to help us out when evaluating this situation. And so doing this, let's go ahead and write down what the first derivative is. So partial over partial z of a squared over a squared plus z squared to the 3/2 power is going to be equal to, well, first we have this 3/2 power, so it'll come out front, 3/2 minus 3/2, right, because it's in the denominator. The thing in the denominator gets lowered by 1, and so this will be z squared to the 5/2, and we're going to get a 2, the derivative of what's inside. The derivative of what's inside is 2z, and so this will be a squared, and we're going to get a 2z out of this. And so the 2's go away. I still have the minus sign, I guess. And there we go. And so this is going to be minus 3a squared z divided by a squared plus z squared to the 5/2. So I can immediately write down what the first derivative, or what the first partial z of b, of r, is going to be. I'm going to factor the 3 out, and that's it, and the minus. So minus 3 mu naught I over 2. And then I'm going to get a squared z over a squared plus z squared to the 5 halves minus, so that's that minus sign right there, a squared d minus z divided by a squared plus the quantity d minus z squared of 5 halves z hat. Now we just keep moving on with this problem. Just keep going down and chugging through this second derivative. Okay, chugging through the second derivative. So the derivative now of a squared z over this a squared plus z squared to the 5 halves, right, is going to be, if it hits the top, this is simply a squared over a squared plus z squared to the 5 halves. But if it hits the bottom, I'm going to minus 5 over, minus 5 halves over a squared plus z squared to the 7 halves. And we're going to get a squared z times 2z on top. 2's are going to cancel, but we're going to get a squared z squared. Multiplying top and bottom of a squared plus z squared in order to put 7 halves in order to make a common denominator, we're going to get a to the 4th plus a squared z squared minus 5a squared z squared divided by a squared plus z squared to the 7 halves. So this plus 1 minus 5, of course, is going to give minus 4. So this is going to give a to the 4th minus 4a squared z squared divided by a squared plus z squared to the 7 halves. Okay. So that's scrunched up there, so you can't read it, but we'll go with it. Just continuing on, we can now write that the second derivative with respect to z of b of r is going to be, I still have the minus 3, I guess, so this is minus 3 mu naught I over 2, and now I'm going to get a squared minus 4a squared z squared divided by a squared plus z squared to the 7 halves, and then I'm going to get a plus here, right? Instead of a minus, I'm going to get a plus, because the minus here is going to get washed out from the minus. So I'm going to get a plus, then a to the 4th, a to the 4th minus 4a squared quantity d minus z quantity squared divided by a squared plus z squared to the 7 halves. Okay. Now, for the final trick, the expression does not find the magnetic field in the first 3 derivatives everywhere along the axis. It's only at the halfway point. We only had to do it everywhere along the axis in order to justify, or in order to take the further derivatives. When I evaluate at the halfway point, look at what's going to happen to this expression. Here I have the same thing again. I have some f of z and some f of d minus z. When I take the derivative, I'm of course going to get an f prime of z minus f prime of d minus z. When I evaluate them both, okay, at z equals d over 2 at z equals d over 2. This is going to give f prime at d over 2 minus f prime at d minus d over 2, which is d over 2, which is 0. And so I already know that one further derivative evaluated halfway between will give 0. And so let's go ahead and let's now do these evaluations. So b of r at z equals d over 2. That's the first one that we looked at. Okay, and so we have it way up here. So this is going to be a squared plus d squared over 4. Okay, and I'm going to get two of them. I'm going to get one here and one here. So this will give us mu naught I a squared over a squared plus d squared over 4 to the 3 halves. Okay. So that's that first evaluation. The second evaluation, partial b over partial z at z equals d over 2, z hat. Well, this is of course going to be 0 for that same reason that we just argued that the third derivative is going to be 0, that when you evaluate it at d over 2, you're going to perfectly cancel out those 2 times. So that's going to always give 0 halfway between them. Then the second derivative, partial squared b over partial z squared, evaluated at z equals d over 2. That is right. Okay, that expression is right here. This, just plug it in. So this is going to give minus 3 mu naught I times a to the 4th minus a squared d squared divided by a squared plus d squared over 4 to the 7 halves power. And of course the third derivative is again going to be 0 because of symmetry. And so here are evaluating the first 3 derivatives for this thing, and the magnetic field and the first 3 derivatives. The next question was find where the first 3 are all vanishing. Find what value of d for them all to vanish. That means I need this expression to be 0, so really I'm only going to look at that. And so I want a to the 4th minus a squared d squared to be equal to 0, which is of course true if a is equal to d. And there you go. And so that's the other condition for vanishing. This is what we call a Helmholtz coil, and what's really neat, right, is the magnetic field is very constant right in the center of a Helmholtz coil. That's what this is showing. This is showing that the magnetic field, its first derivative, its second derivative, and its third derivative are all 0. And so if you were to do a Taylor expansion, you have to go out to the 4th term before you're going to find anything. So as long as you do small variations, the field will look constant in the center. And it's an experimental tool that we use